Rust, it seems to draw a lot from functional programming. Can you unpack that a bit for us, Russ Jackson?
Yeah, absolutely. It borrows ideas about treating functions like data, passing them around, storing them, using them later.
So, like variables, basically?
Exactly. It's powerful because you can build really flexible, reusable code blocks.
So, what are some practical applications in finance?
Say, you have a trading algorithm. You can define different strategies as functions and swap them out easily as market conditions change. This could be key for risk management.
That's interesting. But what about closures? Those sound a bit special.
Closures are functions that can access variables from the surrounding environment. This allows you to create functions that are highly tailored and specialized to a specific task, almost like personal assistants for the larger program.
Like a function that remembers the current stock price for a particular trade?
Right. It's efficient and very important, especially since closures don't need to carry all of that data around, making your code more manageable and quicker.
So, iterators, what do they do?
Iterators allow you to process data step by step, like moving through each item in a list. This is common in processing transactions. Really handy for large datasets.
Like looping through all your customer transactions?
Precisely. Iterators make that process simple and very efficient.
Why is this better than traditional methods?
It can handle huge amounts of data faster, and it's very adaptable.
But this seems like it might be error-prone.
While it has advantages, yes, there are gotchas to watch out for. Potential pitfalls include forgetting to handle edge cases, or issues with infinite loops if the iterator isn't set up correctly, like with an array that has a typo. Knowing the limitations of what you're using is key.
Iterators, closures, how do they connect back to financial stuff?
Think about analyzing customer transaction history. Combining iterators with closures lets you easily filter by specific types of transactions, or analyze their profitability over time in a very clean and efficient way.
So, it's not just about speed, it's about efficiency and readability too?
Absolutely. You can express complex logic in a readable way, which helps with debugging and maintenance, especially critical in a financial application.
What are some common misconceptions about these features?
People sometimes underestimate how fast these are, often thinking that iterators introduce a performance penalty. But they can, in fact, be super quick. You gotta pay attention to details, though.
So, we're talking serious performance gains for the finance industry?
Well, yeah, these features contribute to efficiency and reduce overhead. This is vital in financial operations where speed and accuracy are essential.
Are there situations where you might not use these functional styles, though?
Sure, sometimes a more imperative approach is simpler for smaller tasks, or when you just need one straightforward way of tackling a problem.
Thanks, Russ Jackson. Great insights. This has been super helpful. Rustclosures. Sounds interesting. Tell me more about these anonymous functions, Russ Jackson.
Yeah, closures are cool. Think of them as little, reusable bits of code you can create and use in different parts of your program.
So, they're like mini functions?
Exactly. But they can do something even functions can't. They can remember values from the surrounding code.
How's that work? Can you give me a real-world analogy?
Imagine you're a chef. You have a recipe, a function, that needs specific ingredients, values, to work. A closure is like a recipe that remembers the ingredients it was given when it was first created. It doesn't need you to specify them every time you use it.
So, it's like having a personalized recipe?
Precisely. You write the basic recipe once, and then you can adjust it for different situations by providing different values when you create the closure.
That's powerful. How does this relate to code reuse in financial modeling, for instance?
Say you need to calculate different metrics for different portfolios. A closure can encapsulate the logic for calculating, say, portfolio beta. Each time you use it, it can use the portfolio's specific data.
Makes sense. So, how is this different from just passing variables to a regular function?
A function takes in values but doesn't remember them later. A closure, on the other hand, remembers those values. It has a sort of memory about how it was created.
So, closures capture the environment, but how do they impact performance?
Capturing the environment adds a bit of overhead. It's not quite as fast as a regular function, especially with large datasets. But the benefits of code reuse, flexibility, and customization often outweigh the slight performance cost, and can actually be helpful in financial modeling to handle complex situations.
What happens if you try to use a variable outside of the scope where the closure was created?
Well, that's a tricky area. If a closure needs a value that's only defined later, it won't compile. This kind of enforced scoping helps prevent bugs, particularly in larger systems.
So, closures are great for reusable code, but aren't perfect. There are limitations?
Exactly. There are performance trade-offs, and you need to be mindful of scope. But if used carefully, they're a very powerful tool for flexibility and reusability.
That all sounds useful, but what might some common pitfalls be?
One pitfall is trying to use a closure with values that aren't readily accessible, or accidentally capturing too many values in the closure, adding too much context to it.
So, how do we balance the power of closures with good programming practices?
It comes down to understanding your problem, carefully defining closures, and ensuring that you're not accidentally capturing values that aren't needed. For instance, you want to make sure there are no unintended dependencies from a closure to parts of the program that can be changed later.
Got it. Closures seem like a valuable tool, especially in applications requiring customization and code efficiency.
Definitely. It can be particularly useful in financial modeling because you can tailor specific computations for varying situations without constantly rewriting code.
I understand that now. Thank you. Russ Jackson, thanks for joining us. So, we're looking at refactoring this workout generator. What's the deal with this expensive calculation? And why are we worried about calling it twice?
Yeah, Matthew. The problem is performance. Imagine that simulated calculation is actually pulling data from a database or doing a complex calculation involving thousands of data points. That's going to take some real time, so calling it twice is definitely something we want to avoid.
Right, so this code is doing the calculation and then using the result twice. How's extracting it to a variable help?
Well, storing the result in a variable means we do the expensive calculation once, store the result in a variable, and then reuse that result in multiple places.
So, that's the refactoring part, but it still seems like it's calculating the result no matter what. Can you explain why that's a problem now?
Precisely. The code now calculates the result, even when it doesn't need it. That's less efficient.
Okay, so we're calculating something expensive, even when it's not needed. That makes sense. How do closures come into play here?
Closures allow us to encapsulate code and only execute it when we actually need the result. They're like little containers of code that can be used only when necessary.
So, instead of always calling the calculation, closures allow us to determine when the calculation happens, right?
Exactly. Imagine a function that returns a value, but that value depends on some other action. A closure can let us only run the action when the value is needed.
Intriguing. So, closures are essentially a way to avoid unnecessary work. Like, what about financial applications, for example?
Absolutely. Think about risk assessment models. In finance, you have very complex calculations, but you may only need them for a certain type of trade or under specific market conditions. A closure helps you encapsulate the calculation logic and trigger it only when and where it's strictly necessary, optimizing resource utilization.
So, closures are crucial for performance in high-performance financial applications?
Definitely. Imagine having a trading algorithm that performs a complex evaluation based on market indicators or economic analysis. If you always run the calculation, it can slow down the response time for orders. Using closures, you can encapsulate complex calculations and only evaluate when it impacts decision-making.
So it's about precision and execution control. We only run what we need when we need it.
Precisely. Closures allow that controlled, necessary execution, leading to better performance and potentially more efficient operations, like a trading algorithm responding swiftly.
Great. Thanks for the breakdown, Russ Jackson. This clarifies how closures can be a crucial optimization in financial and other applications requiring precise and responsive execution.
You're welcome. It's a valuable technique in optimizing code for performance, and in our case, it leads to a more efficient workout generator.
Russ Jackson, welcome back. We're diving deeper into closures now. Can you explain the core idea behind using closures to store code?
Sure, Matthew. The key is efficiency and code organization. Instead of calling a function, like simulated_expensive_calculation, every time we need its results, we can define a closure once, encapsulating the code.
So we're defining a kind of mini function and storing its definition, not the result?
Exactly. Think of it like creating a blueprint for a calculation, rather than building the actual structure each time. This is hugely important in performance, especially when dealing with tasks that take time. Imagine a financial model that calculates risk. If we recalculate each time we need the result, it'll take forever.
So how does this closure syntax work?
It's like a compact function definition. The number part defines the input parameters. The curly brackets hold the code within the closure. The result of the last line, not ending in a semicolon, is the value returned by the closure.
And how do we call this stored closure?
Just like a regular function, you call it by the variable name, with the arguments in parentheses.
Okay, so we've improved performance. But in the example, it still gets called twice in one if block. Why is that?
You're right, that's a crucial point. Our code is still doing the calculation twice, which is precisely the problem we're trying to avoid. We'll explore how to fix that to prevent redundant calculation in the next section.
So closures let us define the code and store it in a variable rather than the result, making the code reusable and potentially efficient.
Yes, and it's important to understand the connection to financial systems. Closures can greatly improve the performance of complex algorithms used in financial calculations like portfolio optimization or risk management. Imagine having to rerun intensive calculations every time a user interacts with the system.
Let's talk about the lack of type annotations. Why are there no type annotations for parameters within the closure?
The compiler can infer the types from how the closure is used. The context often makes the type clear. If it is unclear, you can add explicit type annotations.
This closure technique, from the perspective of optimization in a financial system, is it a must-have?
Absolutely. This is a common technique in optimized financial software. When you need to call expensive operations multiple times, you want to avoid redundant work.
And what about potential pitfalls or things to watch out for when using closures?
Be mindful of borrowing rules. When dealing with external resources, closures need to follow borrowing guidelines to avoid dangling pointers and other common errors. Financial applications demand extreme precision.
So, closures are a significant tool, especially when dealing with complex calculations in financial modeling and performance-sensitive systems.
Precisely, Matthew. It allows us to encapsulate the logic for later use without repeating ourselves. It really helps us to build efficient and robust code bases for financial analysis.
Thanks for clarifying these nuances, Russ Jackson.
My pleasure, Matthew.
All right, Russ Jackson, let's dive into closures. So, closures, are they like mini functions?
Yeah, mini functions, but without the explicit type declarations. Think of it like this. Functions are like, formal contracts, specifying exactly what they take in and what they return. Closures are more like notes for yourself, inside a specific context.
So, they're more flexible then?
Precisely. The compiler can usually figure out what type they're taking and returning based on their usage. It's like an intelligent guess and check.
But when it can't, right?
Exactly. And that's where explicit type annotations come in handy.
Can you give us an example of a closure and a similar function?
Sure. A function might be something like adding 1 to a number. You'd explicitly define the input type as a U32 and the return type as a U32. A closure doing the same could drop the type declarations and still work, as the compiler can infer.
So, why omit the type declarations?
Well, for short, self-contained bits of code, type annotations become more noise than value. It's like writing out every ingredient in a simple recipe.
Right, efficiency and conciseness.
Plus, closures are often very specific, used inside a small part of a program, whereas functions are part of a wider interface. That means closures don't need such a strict, public contract.
Interesting. So, if the type isn't specified, what happens if you use a closure with different types?
The compiler will complain. It won't let you call it with different input types because once the first call sets the types, they are locked in. It's a strong typing world, a very important aspect of Rust.
So, A closure that accepts a string can't suddenly accept a number?
That's correct. The type is fixed after the first use.
And that's the fundamental difference?
Yes, exactly. The compiler infers the type from the first usage, making it easier to work with.
Imagine a financial application. How could this affect calculations?
If you're working with stock prices, you might use a closure to process data, say, to calculate an average price. If you call it with stock prices of type F64, you can't suddenly change it to a type of string without a compile time error.
So, it enforces correctness?
Exactly. It enforces the correctness and data integrity of your calculations at compile time, saving a headache later. You're basically preventing incorrect calculation types.
But if a closure is truly a local helper, what if I need to pass in different types, say for different use cases?
You can use generic types, just like with functions, to add flexibility, allowing the closure to work with different types if you really need to. You can create a closure which can work with many types.
So, it's a balance between conciseness, flexibility, and safety?
Absolutely. The compiler can do intelligent deductions for most closures. So, for small, focused tasks, the conciseness of inferred type shines. For more complex tasks, or interface definitions, type annotations bring clarity.
Great. That makes a lot of sense.
So it's like a supercharged mini-function, super efficient when used appropriately.
Thanks, Russ Jackson. That clears up a lot about closures in Rust. Hey, Russ Jackson, let's talk about storing closures in Rust. You've got a cool new trick using generics and the FN trait. Can you break this down for us?
Sure, Matthew. We're trying to make our workout generator more efficient. The old way was calling that slow calculation multiple times. We can avoid that by saving the result.
So, cache the result? How does this new approach work with closures?
Exactly. Instead of repeated calls, we create a struct to hold the closure and its result. Think of it like a little container for the calculation.
So, how does this container deal with different types of closures? I mean, what if we need to store a different function type?
That's where generics come in handy. We use a generic type T to represent the closure. The FN trait is our key. It ensures the closure has the specific signature we need.
The FN trait? Explain that.
The FN trait defines a contract for a callable entity. Essentially, it says, this thing can take input and return output. There are similar traits fnmut and fn-once for mutable and once-use closures, but fn suffices here.
Okay, I'm getting it. So the struct is like a little box. The box can hold different types of functions that take one U32 and return one U32.
Exactly. The box, which is the struct, can hold different closures as long as they match the fn U32-U32 trait. This is like a contract, and it tells Rust exactly what kind of closure is allowed inside.
How does this avoid unnecessary recalculations? Give me an example.
Well, the struct has an option for the result. If the result is already there in the sum variant, great. We use it. If it's none, we calculate it, put it in sum, and remember it. So any subsequent call gets the cached value, saving us that slow calculation.
This sounds like memoization. I see how this improves performance.
Exactly. Memoization. We're optimizing by storing a value for future use, like a financial institution remembering historical rates for calculating loans. It's a powerful technique.
So, cache your struct, right? How about using a t-type in place of a function? Can it be a different kind of calculation?
The t needs to be able to match the fn trait. If the type of t cannot fulfill the trait, it will cause a compilation error.
How does this help financial applications? A simple example?
This is great for financial modeling. Imagine you need to calculate interest rates repeatedly based on different conditions. Caching the result for each set of conditions would speed up your modeling significantly.
Great insights. Can you talk about potential downsides? Any pitfalls to watch out for?
Sure. You need to carefully consider the frequency of changes to inputs. If inputs change frequently, caching the results might not be as advantageous.
Excellent explanation. So, using generics, we create a reusable caching mechanism for closures in Rust with fn, fnmut, or fn-once that speeds up calculations.
Exactly. Now we can write more efficient and organized code by abstracting away the caching logic, focusing instead on the core workout generation.
Russ Jackson, thanks for joining us today. Let's talk about caching in Rust. We got this cacher type. What are its limitations?
Sure, Matthew. The cacher we have right now, while useful, has some pretty tight constraints.
Tight constraints? Tell us more.
Well, it's designed to cache the results of a function. But it only works if you're always passing the same argument. Think of it like a vending machine. If you always want the same soda, it works perfectly. But if you try to get different sodas, it's gonna be a problem.
So, it assumes consistency in the input?
Exactly. The current implementation only remembers one value. It doesn't know how to deal with different inputs. It's like a super-specific calculator that only knows how to handle one specific problem.
And if I give it a different problem?
It just spits out the same old answer, even if it's wrong for the new problem.
That's not ideal. What's the other problem?
The other limitation is rigidity in the types. The cacher is very specific. It needs a U32 as an input and returns a U32. Imagine trying to cache currency conversion rates. You need to store strings and get back numbers of a different type. The cacher doesn't easily support that.
So it's a one-trick pony?
Yeah, for now. It needs to be more adaptable, to support more complex inputs and outputs.
How can we fix that?
We could use a hash map to store different input-output pairs. Instead of just one value, it keeps track of inputs and their associated outputs. And, crucially, we can make it more generic to handle a broader variety of types. Think of it like a highly configurable, adjustable vending machine that can sell different products, not just soda.
So, a hash map to store the results and generic types to handle more diverse functions. That sounds like a more robust solution. Are there any common mistakes developers might make when working with a caching mechanism like this?
Absolutely. A common mistake is forgetting to handle potential errors. What if the closure panics? You need to account for that or risk unexpected behavior. It's crucial to gracefully handle any potential failures within the closure.
Sounds like a lot of considerations, but also really important.
Absolutely. A good caching mechanism, well designed, can be a powerful tool. We just need to account for these edge cases and avoid common pitfalls.
So, you're saying more generics and a hash map would help address the problems we are facing?
Exactly. We need the flexibility to cater to various data types, and a hash map to handle diverse input values. And of course, good error handling.
Thanks for breaking that down, Russ Jackson.
My pleasure, Matthew.
Hey, Russ Jackson, welcome back to the show. Today we're diving into iterators in Rust. Can you give us a high-level overview?
Sure, Matthew. Iterators are like specialized delivery services for data. Instead of manually fetching each item one by one, iterators handle the process for you.
So, they automate the process of going through a list?
Exactly. They take care of the looping and checking if there are more items. This is really useful because it keeps your code cleaner and less prone to errors.
How does this work in Rust? Can you show us a simple example, like fetching numbers from a vector?
Rust's iterators are lazy. They don't do anything until you ask them to. Imagine you've got a package of items, and the delivery service won't move until you tell it to. The code just creates the iterator. It does nothing else yet.
So, you're saying we need to do something with that iterator?
Yeah, we use methods on that iterator object to consume the data. Think of it like instructing the delivery service to bring the package to your door.
Okay, show me how we create one and then get the data from it.
Let's say we have a vector, v1 equals vec, 1, 2, 3. We create an iterator with v1.iter. This is just setting up the delivery service.
So, what's the next step to actually use the data?
You can then loop through it, for val in v1.iter, println, got, val. This tells the delivery service to bring each item to you, and you print it as you get it.
So the for loop is where the iterator actually does the work?
Precisely. The for loop, when using an iterator, is automatically handling the steps to go through each item. It's not actually looping through indexes. It's using the iterator's methods.
That sounds pretty powerful. Any real-world financial applications?
Absolutely. Imagine processing transactions from a database. You could use an iterator to go through the transactions one by one and calculate total revenue. Or you can filter transactions by specific dates or types, applying that iterator logic to a subset of the data.
So, it's like a super efficient way to process large datasets.
Yes, it makes handling large datasets in financial or other applications much more efficient and less error-prone. You don't have to worry about indexes or manual looping.
What if you have to calculate the sum of all the numbers?
You can chain methods to perform calculations, like v1.iter, sum, which calculates the total sum.
What happens if you want to look at items that meet a particular criteria, e.g., numbers 2?
You can use filter, which is another iterator method.
So, iterators are powerful for both simple and complex data operations.
Yes, they're a fundamental part of Rust's functional programming style, optimizing code efficiency and robustness.
This is really helpful. Thanks, Rust Jackson. Rust Jackson, welcome back to the show. Today, we're diving into iterators in Rust. You've been talking about custom iterators. Can you explain how we're using the next method now?
Sure, Matthew. We're showing how our custom counter iterator works. The next method is crucial. It's like asking the iterator, what's the next value?
So, it fetches the next value in a sequence, like pulling items from a queue?
Exactly. And importantly, the next method returns an option. This is super important in handling the end of the sequence.
An option? What's that?
It's a way to represent either a value, some value, or nothing, none. If there are more values, it gives us the next one. If there are no more values, it signals that with none.
So, the next method is like a gatekeeper, making sure we don't try to get a value that doesn't exist.
Precisely. It prevents errors by indicating when the iterator is exhausted.
The code example, it seems like it calls next repeatedly?
Yes. You call counter.next repeatedly in the test. Each call advances the iterator to the next value.
And what do the assertions do in the test case?
They check if the values returned by next are correct. For example, the first assertion checks if the first call to next returns some 1. This verifies that our implementation correctly retrieves the sequence's first element.
So, we can use this to iterate over a custom sequence of numbers, like counting from 1 to 5?
Exactly. This is powerful. You can use next with any iterator, whether it's built-in or custom.
How would this be used in finance? Like, imagine you need to iterate over transaction IDs in a large database.
You could create a custom iterator that pulls transaction IDs from your database, one at a time. Next would fetch each ID, and you could process it.
So, we don't have to fetch all the IDs at once. We just grab them as needed.
Right. This is super important for efficiency, especially with big data sets.
What happens if you try to call next when the iterator is empty?
You get none.
Could you elaborate on the critical role of next in this scenario? Why is this design choice important?
The next method is paramount because it gives you granular control. It's about efficiency and safety. Imagine if next didn't return none when exhausted. You could potentially crash your program by trying to get an element past the end of the collection.
Okay, so calling next repeatedly advances the iterator to the next element, and if no more elements exist, it returns none. This clearly demonstrates the iterator trait in action.
Yes, it's a fundamental aspect of iterators. You'll find the same pattern in many different iterator implementations.
Great, Rust Jackson. Thanks for the breakdown. This was super helpful in understanding custom iterators and the vital role of the next method.
Thanks for having me, Matthew.
Rust Jackson, welcome back. We're diving deeper into iterators today. So, you've shown us how to create our own custom iterators. Now what?
Yeah, Matthew. Once you've defined next, you unlock a whole toolkit of iterator methods.
Like what? Give me a concrete example.
Imagine we have a counter iterator. We can chain operations on it. Say we wanted to pair up values from two counter s, skip the first one from 1, multiply them, keep only multiples of 3, and add up the results.
Wow, that's a lot of steps. How do we do that with the iterator methods?
Using zip, we can combine the counter s, skip 1, skips the first value, map multiplies the pairs, Filter keeps only multiples of 3, and finally, sum adds them up.
So, it's like a pipeline, each step refining the output.
Exactly. The magic happens because the standard library's iterator methods are built on next. They know how to handle the next element.
I see. So, zip combines values from two iterators.
Precisely. But if one runs out, it stops. So, that's why we only get 4 pairs.
I see. So, if one iterator finishes, the other doesn't get used? What happens if they have different lengths?
Right, one iterator reaching the end makes the zip process stop. The counterexample just happens to stop with a short list, which isn't very helpful in real-world financial data analysis, for example.
Let's say we have a situation where we have two iterators that might not be the same length. How would we proceed?
Well, you'd want to be mindful of edge cases, like using zip with iterators that could potentially have different lengths to get the most relevant information.
So, the zip method plays a crucial role in the entire process.
Exactly. You've got different lengths. You'll want to explore options other than zip. It helps you deal with the different cases that arise.
What happens in a scenario where we have an iterator that doesn't terminate? An infinite loop?
You're touching upon a crucial point. Infinite iterators need to be handled carefully to avoid infinite loops. If the length isn't definite, you might use take to restrict the number of elements processed, or otherwise adjust your pipeline.
So we can control the extent of what we receive from the iterator.
Absolutely. That's the key to preventing unexpected behavior.
Is there anything special about the example in the code snippet, besides the combination of operations?
The example showcases how different iterator methods compose elegantly, providing a succinct way to achieve a specific outcome.
Cool. So, this shows us how the design of iterators influences our ability to manipulate data efficiently.
Absolutely. Iterators are a powerful part of Rust's functional programming style. They make data processing straightforward and elegant, which is super useful, especially in financial contexts where you might have data in various formats.
Makes sense. Thanks for breaking it down, Russ Jackson.
My pleasure, Matthew.
Russ Jackson, great to have you back. We're diving deeper into I/O now, and iterators seem crucial. How exactly do iterators improve our config? New and search functions.
Yeah, Matthew. Iterators basically let you step through a sequence of data, one element at a time, without needing to load the whole thing into memory at once.
So, like a conveyor belt of data?
Exactly. Instead of loading all your configuration files into memory, you process each line as you need it.
So, in our config, new, maybe we don't read the whole file at once, but just one line at a time?
Precisely. Imagine a massive spreadsheet. Loading the whole thing is slow and memory-intensive. With iterators, you grab just one row, process it, move to the next. Much more efficient for big files.
But how does that translate to improved searching?
For searching, you can use an iterator to filter through each line and check if it matches your search criteria. So, no more storing the entire file. You just look at one line at a time until you find the answer.
So, does this speed up our financial applications, where we might be processing transactions from huge databases?
Absolutely. Processing massive transaction logs becomes much more manageable. Iterators, if properly implemented, avoid loading the entire database into memory.
Sounds like a huge performance boost. Any pitfalls to watch out for? Like potential memory leaks?
Potentially, but if you use iterators correctly, you avoid holding onto massive data in memory. It's about using iterators wisely to avoid creating temporary data structures that hold up the entire dataset.
So, how will we avoid these pitfalls? What are some good practices?
Using iterator adapters like filter, map, and take are really key. These operations don't need the whole dataset at once to do their work. You can do operations on a portion, effectively avoiding building huge intermediate data structures.
Great points. So, iterators basically allow us to process huge datasets line by line, thus avoiding memory issues in config, new and search, while also making code more readable.
Right. Think of it as streaming data. You just process a stream without accumulating everything at once. It's a big shift in thinking, but it's a game changer.
What if you only need a certain number of entries from that stream?
Iterator adapters handle that, too. You can take only a specific number of elements, or skip over a certain number. This allows targeted filtering, making your code more concise.
That's awesome. But if our search criteria change, how flexible are these iterators?
Well, a big strength is that you can chain iterator adapters. You might filter and then map and then take. You're tailoring the stream for your needs, without having to completely recreate the data structure or algorithm.
So, iterators improve efficiency and code readability for huge datasets. That makes a lot of sense.
Indeed, Matthew. This is something we consistently see in financial applications. The way we handle large datasets directly impacts performance.
Thanks, Rust. Really helpful. All right, Rust, let's talk about this config struct. We're trying to avoid those clones, right?
Yeah, Matthew. Cloning strings is expensive. Memory allocation, we want to avoid it. It's like buying a new house when you could rent one, especially when we have a better option.
So, how do we get rid of the clones?
We're switching from borrowing a slice of strings to taking ownership of an iterator. This way, we can directly move the strings into our config struct without making copies. Think about it like borrowing versus buying.
Okay, but why is an iterator better here?
Well, iterators are awesome for processing collections. They give us access to the data without needing to index into it. It lets us control the flow. Imagine a pipeline of data. An iterator is like the conductor.
How's it avoid borrowing? By owning the iterator?
Not the iterator itself, but the items in the iterator. Previously, we had to borrow the strings from the slice. By taking ownership of the iterator, we can move the actual data into our struct.
So, we're saying the iterator directly gets the ownership of the strings?
Exactly. We get the strings into our config, preventing that unnecessary copying. It's a cleaner, more efficient way to work with data.
How does this relate to, say, a financial application?
Think of data coming from a financial database. Using iterators, you can process transaction data without making multiple copies, saving resources.
What if the iterator is empty? Error handling?
Good point. We check the iterator for emptiness. And if it's empty, we return an error instead of trying to access values that don't exist.
So, the iterator makes it clearer what the function is doing?
Much clearer. It directly shows intent, consuming data instead of borrowing. It's like having a clear roadmap for how you're moving data.
Does this only work for collections of strings, or is it broader?
It's great for working with any collection, anything that can be iterated over. Numbers, structs. Very flexible.
Sounds efficient. What about performance?
This will dramatically improve the performance of our code. Eliminating those clones means no extra memory allocations. It's like driving a fuel-efficient car instead of a gas guzzler.
So, the function takes an iterator instead of a slice?
Yes, the function takes ownership of an iterator, avoiding unnecessary copies, enhancing efficiency and readability. It's like a smart, direct transfer instead of roundabout borrowing and cloning.
What are some common mistakes people make when using iterators?
Not handling empty iterators is a big one, or forgetting the ownership transfer.
Okay, so clear error handling and understanding ownership are key.
Absolutely. Iterators are powerful, but they must be used carefully.
So we're essentially using iterators for control flow and data processing?
Precisely. Controlling how data moves and avoiding unnecessary copies.
This approach sounds super practical. Thanks, Rust. Okay, Rust Jackson, let's talk about this new way of handling command line arguments. Passing the iterator directly. What's the deal?
So, instead of collecting all the command line arguments into a vector, we're now passing the iterator itself to the config constructor.
So, we're just giving it a stream of data, not the whole dataset at once?
Exactly. It's more efficient, especially for very long lists of arguments, because you only load what you need. It avoids building that big vector in memory, which can be really memory intensive. Think of it like a pipeline.
A pipeline? Like for data processing?
Right. You process the arguments one by one as you get them, instead of loading everything at once.
So, how does that change the config constructor?
We change its signature to accept an iterator instead of a slice of strings. This is crucial because env, args returns an iterator, not a vector.
And how do we work with this iterator? We still need to get the actual arguments, right?
Yes, but now we iterate through the iterator, in the new config, new function.
So, it's more efficient and memory conscious, but also elegant.
Exactly. We're being more mindful of the system resources while still being very expressive in how we handle the data.
Interesting. What are the potential downsides of this approach?
Well, you might need more code to process items sequentially, but if the data is extremely large, memory is significantly improved.
Makes sense. How does this connect to, say, financial applications?
Imagine processing a massive order book or stock market data. By not loading the entire dataset into memory, you can handle truly massive datasets without crashing the program due to memory issues.
So, it's about managing memory usage in the face of vast amounts of incoming information.
Precisely. And it's also about writing more expressive, flexible code, using the power of iterators for efficient data handling.
Okay, good point. What if there are errors? How do we handle invalid arguments within the iterator?
The result type, used in the new config, new function, is perfect for error handling. We use unwrap_squirrels to catch and gracefully deal with invalid input, preventing program crashes.
Okay, so in short, this is all about handling input in a more efficient and robust manner, especially with potentially very large amounts of input data, while keeping the code easy to understand.
Exactly. It's all about resource management and maintainability, a crucial aspect of robust applications.
So, is there a case when not to use this method?
Yeah, if the input data is very small, collecting it into a vector might be marginally faster. But the efficiency gains are enormous as the dataset increases.
Good insights. So this iterator-based approach lets you handle huge amounts of data, which can be crucial for financial applications, you know?
Absolutely. It shows how even seemingly small changes in coding style can lead to a big impact on efficiency and scalability.
Thanks for the great explanation. Russ Jackson, we're diving into iterators in Rust now. So, why are we using next instead of indexing?
Well, Matthew, indexing can be tricky, especially when dealing with potentially incomplete data. It's like trying to grab a drink from a bar with your eyes closed. You might get the wrong one or the wrong amount.
Right, so next is more safe?
Precisely. It lets us get the next item in the sequence if one is available. It's safer and more robust because it handles the case of a sequence potentially ending before we expect.
How does that translate into, say, getting command line arguments?
Imagine you're building a program that needs a query and a file name. Using args.next ensures we get them one by one. If someone runs the program without a file name, it won't crash. It returns an error.
Okay, so it gracefully handles the lack of arguments instead of panicking?
Exactly. It's essential for writing reliable programs, especially those interacting with external sources like command line input. Think of it like a waiter who brings you the next item on your order. You don't try to grab a dish that isn't there.
So, the first args.next basically skips the program name?
Absolutely. The first argument is always the name of the program itself. This call just moves us past that. You know, it's like skipping the menu when you want the drink or food.
And if there's no query? No filename? How does it prevent the program from breaking?
The code uses match statements to check for some, there's a value, or none, there isn't. If next returns none, it returns an error.
Interesting. A built-in safety net. This approach feels safer than indexing directly?
Yeah, imagine what could happen if the arguments were missing. Your program could be vulnerable. The iterator approach is more robust because it checks for validity at each step.
Great point. So, it's about reliability and preventing crashes?
Absolutely. It's also more flexible. You can easily add more robust error handling.
And how might this apply in a financial application?
Well, imagine fetching stock data. If the API returns unexpected results or gives incomplete data, you wouldn't want your program to crash. Handling the API's output gracefully, using something like Next, is crucial for stable financial applications.
So, iterators are essential in preventing common program errors, and that's why they're built into Rust?
Exactly. Rust's designers prioritized reliability and safety, and iterators play a key role in achieving those goals.
Makes sense. Thanks, Russ Jackson.
You're welcome, Matthew.
Hey, Russ Jackson. Thanks for joining us today. We're diving into making code clearer with iterator adapters in Rust. Let's start with the basics. What are iterator adapters, and why are they useful?
Iterator adapters are, well, they're like superpowers for iterators. They let you modify how an iterator works without rewriting the whole thing. Think of it like plumbing tools. You can use them to filter, map, or chain together different data streams in a really elegant way. They're really powerful for concise code.
Okay, so you're saying they make code more readable?
Exactly. Instead of explicit loops, you're describing the transformation you want the data to undergo. It's more expressive.
Can you give an example of how to use them in a financial application?
Sure. Imagine you're tracking stock prices. You've got an iterator over all historical prices. You could use a filter to get only the prices above a certain threshold, say, above $100. Then you could map those filtered prices to the percentage change, relative to the previous day. This keeps the logic clean and avoids messy loops and intermediate variables.
Okay, that makes sense. Let's look at the code snippet. It's about a search function. What are the key differences between the original and the iterator-based implementation?
The original search function uses a mutable vector to store results. The iterator-based one uses filter and collect to directly build the vector. It also avoids mutating state, which makes it thread-safe in the future.
That means if you wanted to parallelize the search, you could do it more easily with the iterator version?
Exactly. In the functional approach, we're passing values through a series of transformations. That's different from managing shared mutable state. Parallelism can often be implemented without worrying about race conditions.
So, the iterator approach is potentially faster because it avoids the overhead of building intermediate vectors?
While the original version might be slightly faster in very simple cases, in most cases, you're right, the iterator approach is more performant and much more readable. The compiler does a lot of optimizations. But more importantly, it's much easier to reason about and maintain.
Interesting. Are there any downsides to the iterator-based approach?
Well, it might be a little harder to learn at first, because you need to understand the iterator adapters and chain them together. But it's definitely worth the learning curve. You can often discover that you can use iterator methods that are efficient and readable, often producing a speed gain over standard loop methods.
So, is the iterator approach always better?
Not necessarily. In very, very simple cases, the iterative approach may be faster, but readability and potential future scalability are often critical. The compiler does a fantastic job of optimizing the iterator approach in most cases, which is why it's usually recommended for efficiency as well. Think about future maintenance and enhancements. That often outweighs tiny performance gains.
Excellent points. So, in a financial context, if you're working with large data sets of stock prices or trading data, using iterator adapters for searching and filtering would usually be a better design choice. Thanks, Russ Jackson.
My pleasure.
Russ Jackson, thanks for joining us today. We've been talking about I/O improvements, and now you're mentioning closures and iterators. Can you unpack these for us?
Sure, Matthew. Closures and iterators are like powerful tools in Rust, borrowing ideas from functional programming. They let you express complex logic concisely, but with the same speed and efficiency as lower-level code.
So, they're like shortcuts, but they don't slow things down?
Exactly. Rust is committed to zero-cost abstractions. This means that the way you write code, with closures and iterators, doesn't change how fast your programs run. It's about writing cleaner, more understandable code, not sacrificing performance.
You mean like loops, but fancier?
Well, they're more general. Imagine needing to process a list of financial transactions. Using iterators, you can apply actions, like filtering for specific types or calculating totals, easily without needing complex loops.
Can you give a quick financial example? Like finding all transactions over a certain amount?
Absolutely. You could have an iterator that filters your transactions, returning only those exceeding a certain threshold. You write a simple closure to specify the amount. It's powerful for tasks like fraud detection or reporting.
That sounds really useful. But are there any downsides? Any problems or counterexamples?
Well, sometimes you might need a bit more control over the low-level details, and for those cases, you wouldn't use an iterator. You'd handle that manually if you needed extremely precise performance tuning.
That makes sense. So, Rust has a great balance, allowing high-level abstraction without impacting efficiency, something crucial for high-frequency trading systems and finance, right?
Yes, precisely. Think about how you would apply a discount to a large database of products. Using iterators, you apply your logic without slowing down the whole process.
So, closures and iterators, they really boost readability without hurting performance. That's critical for a programming language, isn't it?
Definitely. It's about writing maintainable code that's fast. And that's crucial for any application, including financial systems.
Now, let's move on to Cargo. How does Cargo help share your projects?
Cargo is a package manager for Rust, similar to NPM for JavaScript. It lets you easily distribute your projects and manage dependencies. It's very useful for sharing and collaborating on Rust code.
So, for large financial projects, the modularity afforded by Cargo is essential?
Absolutely. Teams can work on different components of the system, which can then be seamlessly integrated through Cargo's dependency management.
Great. That sounds like a very organized and maintainable workflow.
It is. It makes it much easier to build and share complex projects, even large financial applications.
Thanks, Russ Jackson. That was a really helpful overview.